Hello all, and thank you for joining my session. Today we're going to be talking about AutogadgetFS, which allows you to do USB testing very easily. So for today we're going to talk about a fast crash course about USB, what is AutogadgetFS, and then we will be presenting several demos, which will be like a man in the middle, fuzzers, for both the device and the host, as well as sniffing devices. So my name is Ihab Hussein. I'm a senior security consultant at IOActive, and if you'd like to follow me and DM me on Twitter, feel free to do that. So for a quick USB crash course, USB is short for a universal serial bus, and it starts at speeds as low as 1.5 megabits per second from USB 1 up to 40 gigabits per second at Super Speed Plus and Thunderbolt 3. So for a system to identify a USB device, the USB device should expose some descriptions about itself to the system. So each device has one device descriptor, several configuration descriptors, and each configuration has interface descriptors, and each interface has an endpoint descriptor. So a device descriptor actually tells the system about the vendor ID and the product ID, who the vendor is and what the product is, as well as the manufacturer names and the serial number. And also in the device descriptor, it tells the system how many configurations does this device have. So what is a configuration descriptor? A configuration descriptor is tells that the configuration that's running, what's the max power, how many interfaces, and stuff like that. So what is an interface descriptor? An interface, you think of an interface as a service on your machine, and the endpoints that are tied to this interface are the ports which you connect to send and receive data. So the endpoints are unidirectional, except one endpoint. So the interface descriptor tells what kind of interface is it. Is it a human interface device? Is it a CDC interface? And with this interface descriptor comes down to the endpoint descriptor here. And this endpoint descriptor describes what's the maximum packet size that this endpoint can handle, and what type of endpoint is it. So there are three types of endpoints. The endpoint in, endpoint in and endpoint out are, think of it like a port for direction in, port for direction out, and these are based on the host, not the device. So in, it means the data from the device is going to the host. The endpoint out is the data from the host going to the device. And there is a control endpoint which is called endpoint 0. This is the only bidirectional endpoint, and it's used only by the host to get and set configurations on a device. So what are the endpoint types? There are 4 endpoint types. Interrupt transfers. This has limited latency, and these are used for like mouse devices, and they're also known as stream pipes. And there is isochronous transfers, and these are for real-time data used for audio and video, also called stream pipes, and control transfers, which are only used by the host to set and get information on a device. These are known as message pipes, and they're also called endpoint 0. The last endpoint type is the bulk transfers. These are for large data transfers. They have CRCs for error detection, and they guarantee delivery. These are known also as stream pipes, and you can find these kind of endpoints in printers and scanners. So what is AutogadgetFS? So this is an open source tool that I built. I kept in mind people wanting to assess USB devices as easy as possible. and as cheaply as possible, which is only the price of a Raspberry Pi Zero with Wi-Fi. So you don't really need to know what's happening under the hood, because this is what the aim of AGFS is. It's written in Python 3, and I use a RabbitMQ, so I can ensure that packets are delivered in the right order in the right time. Of course, I use Wi-Fi access. This is why I recommend using the Raspberry Pi Zero with Wi-Fi. So you can test devices anywhere on the internet. So a device can be connected to your machine, and a Raspberry Pi connected to a remote server which you want to be fuzzing or doing a man in the middle. Yeah, so this is why I made it over Wi-Fi. And we use configFS to emulate devices quickly, and you don't need to do anything because AGFS does that automatically, which we will see in the demo. So these are the scenarios, different scenarios you can use with AutogadgetFS. You can do a device-only testing, which is a device directly hooked up to your machine, and you want to sniff the device and fuzz it or something. This is one scenario. Another scenario, which is a minimal AGFS in the middle, which is a device with a computer or a VM running, and a Raspberry Pi Zero, which is connected to the VM, for instance. And you can do a man in the middle between the software that's running inside the VM, which the Pi Zero is connected to, and the device which is connected to your main host. The complete man in the middle setup. So I usually sometimes do that, and I find it giving you a good results. Is you hook a hardware debugger up to your USB device, and on your computer on the other side here, you will be able to have a debugger running attached to the software that's going to be controlling the USB device. And we will see one demo with this and how successful that is. So some capabilities. You can find, select, and attach to your USB device with ease. You can emulate a USB device. Currently, we're only supporting emulation of HID devices, but the roadmap will show that we're going to be simulating any type of device very soon. We can do a man-in-the-middle sniffing also on HID devices at the moment. You can do sniffing, device sniffing. And I have built several fuzzers for you or you can build your own on top of AGFS. We have random-based fuzzers, like dumb fuzzers. We have smart fuzzers, which learn from communications that have happened during a man-in-the-middle attack. You can teach this smart fuzzer the communication that was sent, and it will generate packets based on what it has learned. A describe fuzzer, which the name might change, but just for the demo. So a describe fuzzer allows you to take a packet and select which bytes you want to fuzz, and you can fuzz these bytes either by sending them to the host or to the device. It's up to you. A gadget fuzzer, which creates emulated USB devices with bad information in their descriptors. So it usually crashes software, or you can find nice bugs there. And I will show one in the demo. You can enumerate control transfers. So there are some control transfers that we enumerate by getting the configuration from a device. So instead of you doing things manually, I enumerate them for you. And if there is any sensitive data or something on the device, you would be able to get that. Also, you can replay packets from a file. You can replay packets saved from a USB Lyzer capture. And the way we visually present packets allows you to reverse engineer the communication quite easily, and we will be seeing that in the demo. Also, it alerts you if a device is in DFU mode, and I'm actually putting together a way to actually pull firmware from USB devices through DFU mode. It's not implemented yet, but it's on the roadmap. And also, it alerts you if the device leaks information, if some kind of report that came back doesn't conform with the spec. Of course, you can connect and test USB anywhere on the internet. And finally, you can monitor sudden interface changes, like when you convert your Android phone from normal USB communication to a file transfer or something, you will get an alert that the configuration has changed and the interfaces have changed. It's quite useful in some scenarios. So currently we have a problem with sniffing control transfers that happen from the host to the device. I'm currently working on that. I want to emulate and man in the middle all types of devices, and I want to develop some kind of console or Qt based interface instead of working on the command line. Let's start the demos. We'll be doing the a man in the middle demo, device and host fuzzing and device sniffing, and a little bit more demos as we go. So let's try some demos. Running IPython and importing AGFS, and then we create an instance of AGFS and we call the new project, and then you can give your new project a name. And once you give it a name, it will ask you to select a device, and we're going to select 11, which is the new Vuitton device that will be man in the middle. And as you can see, the first thing it gives you is the device descriptor, and as you can see, there is the manufacturer and stuff like that, and then you have the configuration descriptor, the interface descriptor, and the endpoint descriptors. We need to remove the device from its driver, and then we will be selecting the first configuration, and we don't need to reset the device, and we select the configuration. Now we just write we call the method setupGadgetFS, and we tell it that we're going to use it with the Windows system, and we just select the HID report and we send it to the Raspberry Pi. And once you say do you want to run the gadget, it will pop up on the screen because I'm doing the VM. It's in a VM, and yes, we will connect to Windows. I'm running the software that's going to be controlling the device inside from within a debugger. So because we're going to be testing one of the fuzzers to see a crash happen. The terminal below, we started the router, which is on the Raspberry Pi, and we told it that we connect to the IP 1.3, which is the RabbitMQ IP, and the L is for the length of the maximum packet size, which is 64 bytes. Now we use the method start man in the middle. We give it the endpoint in and the endpoint out, and we save the communication of both the device and the host, because we will be needing it in a future demo with the smart fuzzer. So we run the device, we run the software inside the debugger, and we tell it to connect. Nothing is going to happen until we start the man in the middle. And once we start it, you can see that the device has been connected. And you see from the representation here that we do a diff between packets, so you'd know which bytes have been changed. So if you have data coming by or something, you'll be able to notice it because you will see a lot of red blobs like what's happening now. So this is actually data being transferred from the device to the host, which probably is parts of the firmware. And we will see that once the device has finished loading the firmware and its information in the device. So we tell it to refresh the window here, so we can grab the contents from the of the AppROM and the LD-ROM and the data flash from the device. And as you can see, in a few seconds, it should be coming up with the firmware. And like we said, visually you will be able to see and understand what's happening. So you see the red blobs happening at the moment. These are actually this is the firmware being transmitted from the device to the host. And as you can see, it has finished, and we have all the contents of the AppROM and the LD-ROM and the data flash. So now we disconnect the device and start running the gadget fuzzer to see if we can find bugs in this software. So running the stop man in the middle method will stop the man in the middle. Now we load the msec module to just see if any bugs are exploitable or not. Once we have run that, we start the software again, and we try to connect. Nothing is going to happen because there is no man in the middle happening. But and we call the method start gadget fuzzer. We give it the vendor ID and the product ID, and we have a serial of AutogadgetFS, and we want to generate 20 simulations of 20 emulations of a device. Once you start doing that, and they are sent, you get the exceptions, and we're successful on the first try. And you write exploitable, and we see if this is actually exploitable or not. Give it a few seconds. And yes, the classification is exploitable. Try running it again. Crashes again. So we successfully found a bug in this software. And that's the first demo. And in the middle, and we saved the communication between the device and the host. And now we were going to be using the saved communication from the device to the host and generate packets based on what we have gotten there in the communication, and generate packets based on these patterns. As you can see, the last a few bytes were the same. So when we come to generate these packets, it's going to keep them the same. So we're going to generate 10,000 samples to the direction of the host, and we are going to learn from this communication file. And we're going to use a random engine. We have other engines. You can look it up in the documentation. So you can see that it recognizes that the final character set is hex from 0 to F. And when it comes to send it, you can see that the last blue bytes are the same, which this is what it has learned from the communication. It's always going to have that in the communication. So that's what the smart fuzzer does, is you give it packets, it learns, and it generates based on what it sees. So it could be useful in a lot of cases. Showing the random fuzzer. So we create a new project, and we're going to fuzz an authenticated unlocked only key. So we want to use the fuzzer so we can find functions in the device. So first we do the configuration as we did in the first parts, and we call the method dev_rand_fuzz. We give it the endpoint in and the endpoint out so we can read and write to it, and we set the reset parameter to 1. In case the device crashes, we just call reset and we reset the device so it comes back. And it starts sending random data out, and as you can see in a few seconds it will be hitting functions inside there, and we will have some successful fuzzing. So you can see here the fuzzer sent a packet and it got error, no key set in this slot, and a little bit more. Usually you don't get these timeout errors in other devices, but it's happening here. And you can see that we sent it a packet and we got unlocked. This is what actually unlocks the software. We will see that in another demo. And other fuzz packets gave us more info, and we successfully wiped the U2F private key, invalid RSA slot, no key set in this slot. So the fuzzer actually helps you find functions. So it's pretty useful in a lot of cases, even if you want to crash a device or find functions or whatever. The fuzzer does its job quite well. In this demo, we will be looking at the host random fuzzer. So we're going to emulate a only key device and send random packets to the software without man in the middle or anything. We're just going to generate packets and just try to unlock the interface of the software. So we create a new project and we select 13 for the crypto trust device. We detach the device from the system. We don't reset it, and we choose the first configuration, of course. And we start calling the method setupGadgetFS. And we want it to work with Windows. And we select the second head report because we're going to use the second interface to communicate with this software. Do you want to run the gadget? Yes. And now we have the gadget connected. As you can see, it has become working. And we call the host rand fuzz. We want to send 100 packets with 64 bytes to the device. And as you can see, we send some packets and the software unlocked, as if the key was connected, but there is no key connected. In this demo, we're going to do a sniffing of a device, which is the Genius Easy Pen. First thing we do is import AGFS, and we create an instance, and we create a new project. So, give the project a name, select the device, detach it from the system, and we don't need to reset the device, and we select the first configuration. And once we do that, we are able to call a method start sniffing, which is going to help us sniff the endpoint. And then we go to another terminal and we type tty to get the file name of that terminal, so we can write to it. We paste it in AGFS, and we hit enter when we're ready. And then once we move the pen, you will see the packets coming up, and the diff will show you how the packets are created, so you'll be able to know how to create packets. And that's how device sniffing works. So once you understood how the packets are created, so now we can use the describe fuzzer to create packets and send them to the host. So we took one packet and we told it I want to fuzz the first index, the second index, and the fifth and the seventh index. These I want to fill with random bytes, and I want to send them to the host. As soon as I send them, you will see that in the diff here, you will see that the first, the 0 index, the second, the fifth, and the seventh always change, but the other packets don't. So that's how the describe fuzzer works. In this demo, we will be showing a RFID device that doesn't conform to the spec, and which leaks information when we request its head report. So we start a new project and we select the device. And as soon as we detach it and select the configuration, you will see an alert by AGFS telling you that it's possibly that there is data leakages in the head report. If you scroll up a little bit, you will see that strings like read success, it has been successfully decoded. Such things are important. Maybe the device could leak some secrets to you. And this is why we always read the maximum size of the report. We don't confirm to the spec ourselves, so we can grab some data leakage like this. And this is one of the features of AGFS. I would really thank you all for joining my session here. If you have any questions, please leave them in the chat. Make sure to visit agfs.io for the installation and everything about AGFS. Also, docs.agfs.io has all the documentation and how to use it in case the method names have changed or anything. Also, you can join my Slack channel if you have any questions. And thank you all for taking the time to see my software. Have a good one.